Welcome back to the second video for Tech 293 on Thursday, April 8th. In this video, we're going to talk through the second beam bending worksheet that starts on page 89 of your lab manual. Once again, I'd recommend that you solve these problems yourself first, or at least give it a good shot, and then come back and watch the video and listen to the explanation of them. So I'd recommend, if you haven't done so already, pause this video, try to solve the problems, give them a crack, and then come back and listen to the rest of this video. For these problems in the second worksheet, I don't have these on slides, so I'm going to solve these by paper and pen, or actually paper and marker, as it may be. So with that, I'm going to switch over to the document camera and we'll start talking through the beam bending problems on page 89.
I'm guessing you can't read the text on this page very easily, but it is in your lab manual on page 89, so you can follow along there. The question here says that we have an I-beam shown in figure 1, so here's the cross section, and here is a diagram of the support. So we can clearly see that it is a simply supported beam with a load applied in the middle of the beam. It has a height of 6 inches, that's what this dimension tells us, and a width of 3 inches. The flange and the web are both 1 inch thick. So here's one flange, here's the other flange. This is 1 inch thick, and this is the web, and this is 1 inch thick as well. The material has a flexural modulus, E sub B, of 200,000 psi, and it spans a distance of 8 feet, that's the span. And a single point load of 500 pounds force, so this is 500 pounds force, is applied at the center of the beam. Okay, so we're going to have to solve some different things about this situation. Part A says, what is the moment of inertia of the beam? So the moment of inertia we can calculate by looking at the cross-sectional area. And remember that the cross-sectional area is 6 inches total height by 3 inches width. But then we're going to have to calculate the moment of inertia of this total rectangle and then subtract the moment of inertia for these hollow sections. There are 2 of them. So that's what we're going to do. Remember, the equation for moment of inertia is 1/12 times the base times the height cubed. So what we're going to do to calculate the moment of inertia of the total I-beam, we're going to calculate the moment of inertia of the total solid rectangular section, and then subtract the moment of inertia for each of the hollow sections independently. All right, so what we're going to do is, here's the total shape. So first we're going to calculate the moment of inertia of the whole rectangle, like this shape. We'll calculate the moment of inertia of this rectangle right there. And then after that, we will subtract the moment of inertia of this rectangle right here. And we will subtract the moment of inertia of this rectangle right here. So that's how we can calculate the moment of inertia for sections that are not a solid rectangle or a solid cylinder. We can just subtract the hollow sections. All right, subtract the moment of inertia from the hollow sections. So that's what we're going to do here. We're going to take the moment of inertia of the big rectangle, subtract the moment of inertia of one of the hollow sections, and then subtract the moment of inertia of the other hollow section. So for all of these, we need to be careful about plugging in the value for the base and the height. So for the big rectangle, the base is 3 inches. That's the width. And then the height is 6 inches, and we cube that 6-inch value. And then for the hollow sections, they're the same. And so we subtract 1/12 times 1 inch, that's the base of the hollow section, times the height cubed. So the height is 4 inches. We got that by taking 6 inches minus 1 inch minus 1 inch. So this dimension must be 4 inches. So the height is 4 inches, and we cube it from the equation for moment of inertia. So you plug that into your calculator, and your result should be 43.33 inches to the 4th. That's the moment of inertia for the I-beam section. Okay, part B says, what is the deflection of the beam? Assume that the stress remains in the elastic region. So that is really nice and helpful. that it remains in the elastic region, because that way we don't have to check to make sure it remains in the elastic region. We can go ahead and use our deflection equation, but remember that deflection equation assumes that we are in the elastic deformation region. So it's nice that we can assume that we do remain in the elastic deformation region. That way we can just use that deflection equation and plug in values. So we're going to calculate the deflection of the beam, so we're going to have to find the equation that is relevant for the deflection of a simply supported beam with a point load applied in the middle. There's only one equation for the deflection of a simply supported beam with a point load in the middle, and we look that up, and it is this equation right here. The maximum deflection, that is the point in the beam with the maximum deflection, so that's in the middle. The maximum deflection is equal to 1/48th, that's the constant, times FL cubed divided by E sub B times I. And at this point, we know all of these things. All of these are either given to us or we just calculated it in the case of the moment of inertia. So plug in values. We got 1/48. Plug in the force. We're told that it is 500 pounds force. Plug in the span, L, and be careful about how you plug this in. The way it was given to us in the problem is 8 feet. But if you plug in 8 feet right here, then your units are not going to cancel out, because here you have pounds force per inch squared, and for the moment of inertia, you have it in inches to the fourth. So if you plug in feet right here, your units are going to be all messed up over here. So be careful when you're plugging in units. Make sure they cancel out. So since I have inches down here and here, I want to put this in inches. So convert 8 feet to inches and you get 96 inches. You're going to have to cube that. And then in the denominator, you have your 48 and you have your flexural modulus, which is given to us, 200,000 PSI, which is pounds force per inch squared. And the moment of inertia, we just calculated, and it's 43.33 inches to the fourth. All right, so plug these numbers into your calculator, but also take a look at the units and make sure the units cancel out. So what do we got? In the numerator, we have pounds force. In the denominator, we have pounds force. So these cancel out. And in the numerator, we have inches cubed. And down here, what do we have? We have inches fourth divided by inches squared. So what we get in the denominator is inches squared. And we have inches cubed in the numerator. So inches cubed divided by inches squared in the denominator gives us inches. And that's good because the question is, what's the deflection of the beam? And our answer is going to be in inches. So that's perfect. So you plug that in, cancel out the units, and you get 1.06 inches. Letter C, what force would be required for the maximum deflection of the beam to be 3.5 inches? Assume the stress remains in the elastic region. So once again, that's great that we can assume it remains in the elastic region because we don't have to check. And we can just go ahead and we can use that deflection equation, even though that deflection equation assumes that we remain in the elastic region, but we're good because it says that we are. Okay, so we have our deflection. It is going to be 3.5 inches, and we want to find what is the force. So it sounds like we can go ahead and use that equation for deflection again, and just plug in 3.5 inches for the deflection. So that's what we'll do. Make sure you're using the correct equation. Once again, this is the equation for a simply supported beam that has a point load applied in the middle, and this is for deflection. So this is the same equation as we had up here because they're both dealing with deflection. So this is the correct equation to use. And in this part, part C, we're trying to find the force. So take this equation and rearrange this equation to solve for force. So multiply both sides times 48 E sub B times I, and divide both sides by L cubed, and you get this equation for the force. And now we know all of these things, and so we can just plug them in. With units, once again, be careful, keep your units. So plug in for 48, that's part of the constant. This is the deflection. This was from the question. This says the maximum deflection is 3.5 inches. So this is from the question. And this is the flexural modulus that was given. This is the moment of inertia that we calculated. And this is L cubed. And once again, be careful about how you put that in there, because we have the flexural modulus in PSI, which is in inches, and we have the moment of inertia in inches. So don't put in feet down here. You'll end up with crazy funky units that won't really mean anything. So when you do that, plug these numbers into your calculator, and then let's take a look once again at the units. So we've got pounds force up in the numerator and no pounds force down here. So we're going to have pounds force in the numerator of our answer. What about inches? What are we going to have for inches? So we've got inches to the fourth divided by inches squared. So that leaves inches squared. And we've got another inches in the numerator. So we've got overall, we got inches cubed in the numerator. And we've got inches cubed in the denominator. So the inches all cancel out. And we're left with just pounds force in the numerator. Okay, so plug in that to your calculator and you find 1,646 pounds force as the answer for part C. Okay, then we've got part D. What is the maximum stress? So this is not deflection anymore, this is stress. What's the maximum stress in the beam when the beam is when it deflects by 3.5 inches? Well, that's kind of convenient because we just did a problem where the deflection was 3.5 inches. So keep that in mind. That might be useful. Okay, what's the stress in the beam when the beam deflects by 3.5 inches in the center of the beam? All right, so it's a point load applied in the center. What is the stress when it deflects by 3.5 inches? All right, so it's still a simply supported beam. And we still got a point load applied in the middle, and we're talking about stress. So what is the equation for a simply supported beam with a point load in the center for stress? It looks like that. That's the stress equation for a simply supported beam with a point load applied in the middle of the beam. It looks like that. All right, so 1/8 is a constant from that equation. The F, what is the F? Well, it's not immediately obvious what is that F, but this is what I was saying a moment ago. It's kind of convenient because look at what part C was. Part C said what force would be required for the maximum deflection to be 3.5 inches. So that's exactly what we did in part C. We calculated that F right there. And now we're going to use that F in the process of calculating the stress, the maximum stress in this beam. So we can go ahead and use that F. This is the F that we just calculated in step C of this problem. So if you recall, that was 1,646 pounds force. So we plug that in right here. And the length of the beam, or the span, is 96 inches. Once again, be careful about what units you plug it in so it cancels out with the others. And the height of the beam, remember that was 6 inches. That's the total height of the beam. So you plug in 6 inches up here for H. And the moment of inertia we calculated back in part A, so plug that in, 43.33 inches to the fourth. So you plug in all your numbers to your calculator, you get the numeric value, but what is going to be the units? All right, well, pounds force is in the numerator, but not in the denominator, so we're going to have pounds force in the numerator. And what about inches? Up here we got inches times inches, so inches squared. Down here we got inches to the fourth. So two of these cancel out, well, two of these cancel out with these, and we're left with inches squared in the denominator. So we're going to end up with pounds force per inch squared, and that is the same thing as PSI, which makes sense because we're talking about a value of stress. So that's good. So our number ends up being 2,735, and our units are PSI. Then we have part E. Part E says if the modulus of rupture, remember that's the flexural strength, same thing, is 10,000 psi, what is the maximum load or force that can be supported by the beam before it fails? Okay, so to do this, remember this is a value of stress. Flexural strength, modulus of rupture, those are the values of stress when it fails. So this beam is going to fail when the maximum stress, which is going to happen right here, when that stress value is equal to 10,000 psi. So all we really have to do is take the stress equation, because this is stress, and set it equal to this value, and then solve for the load force. And that's going to be our answer. So once again, got to get our stress equation. This is the stress equation for a simply supported beam with a point load applied in the middle. And what we're going to do is rearrange and solve for F. So take both sides, multiply times 8I, divide both sides by LH, and you get this equation for the force. And what we're going to do is plug in our numbers here, because we know everything in here now. So plug in, that's from the constant. This is the stress value when it's at the modulus of rupture. So when it's failing, this is the maximum stress in the beam. It's the modulus of rupture. So we plug that value in right there. So that's the stress. And this is the moment of inertia. And this is the length. Once again, be careful about the units that you plug in here. This is the total height of the beam from this dimension right here. So we're going to get a number, but what's our units going to be? So we have pound force up here in the numerator and nothing in the denominator. So we're going to have pounds force in the numerator. What about these inches? So up here we got inches to the fourth divided by inches squared, which leaves us with inches squared in the numerator. And we've got inches times inches, or inches squared, in the denominator. So our inches all cancel out. The numerator has inches squared, the denominator has inches squared, so they cancel out. So our units are going to be in pounds force, which is good because we're trying to find a force. And so pounds force is a valid unit of force. All right, so plug all that in and you get a value of 6,018 pounds force. All right, that's going to wrap up today's videos on beam bending review problems. There is a very good chance that you're going to see questions very similar to these on the next exam. So I want to make sure that these concepts are very clear. If you have any questions about them, if you're stuck on some part of the problem, please let me know. Come to office hours, shoot me an email, send me a picture of the work that you've got done so far and explain what you're hung up on. And I can probably help you out pretty quickly just by pointing out something that maybe you're not understanding quite correctly. But hopefully by doing these review worksheets from page 87 to page 89, I think that's a pretty good review. If you can do these comfortably, then you're in pretty good shape. But definitely let me know if there's any questions that come up, and I'll be happy to help you out. So that's going to be it for this time. I'll see you in the lab, and have a good weekend.